Now, I didn't bring it in, but do you guys remember clear back at the beginning of part 3? I guess it was just like Wednesday. Seems like forever. But we said by definition something boils if its equilibrium vapor pressure is equal to atmospheric pressure. Okay, and I didn't go on to, and then we talked about boiling point temperatures, and we said that something that if it's got a high temperature it boils at, that means you must have a lot of intermolecular bonds and or strong intermolecular bonds, and we talked about that. Now we're going to kind of talk a little bit more about what does it mean for a material to have an equilibrium vapor pressure. Okay, I love this. The term equilibrium, anytime you see it, whether it's a physical process like this equilibrium, honestly, and you'll see what I mean here in a minute, all this equilibrium is, and I'm going to put an L and a G. And I'm going to put another arrow going from left to right and right to left again. So what are my L's and G's here?
Liquid and gas.
Liquid and gas, yeah. So chemical equilibrium, this is the equilibrium we're talking about here. Okay, and I'll go ahead and finish that thought. Basically, when you have this sort of equilibrium, whatever that pressure is, okay, that pressure is your equilibrium vapor pressure. Okay.
Is that referring to like the equilibrium vapor pressure is like when it's close to the temperature or the pressure where it would change from gas to liquid?
Nope. I'll show you. I really like this little thing. Okay, the way you look at these figures from left to right is you give it time. So basically what we have in here is a volatile liquid. Okay, water's not very volatile, but I guess a little bit. We'll talk about volatility coming up here. But can you see where the red means evaporation? Okay. So basically that dome jar is a vacuum. There's nothing in that dome jar right there. Okay, we give it a little bit of time, and now we have those little dots there are the blue substance in its liquid state. The gray dots are in its gaseous state. Okay? So here we have evaporation is red. What's blue? What's the blue things? The blue things, what physical phase change? Yeah, blue things are condensation. So evaporation, condensation. At this point, which one do you have more of?
Evaporation.
Right, you have more evaporation than condensation. You are not at equilibrium now, okay, yet. The third one is you've given it enough time, that's why I mean time, okay? Now how would you relate the reds and the blues? They're equal. You have reached equilibrium. How would you describe the matter in its gaseous phase, C compared to B?
Way more gas.
There's way more at equilibrium. But I'm here to tell you, and I'll try to convince you or you can read yourself, this is this funny looking thing, and I've drawn one before. This is my pressure gauge. Okay, I'm going to go ahead and put a little, it's a needle thing, right? So I'm going to go ahead and put a pressure there. It's going to remain constant, okay, at your equilibrium vapor pressure. Now, and this kind of goes back to one of the things Rhonda said, we're going to see that this depends upon temperature. I'll put T is equal to question mark. If you change the temperature, you change the equilibrium vapor pressure. Okay, so that's how that works. Cool. So this is looking at equilibrium vapor pressure again. Now, I don't know if you guys recognize this, but this is our liquid mercury barometer. So if you have a liquid mercury barometer like this, it's open at the bottom and closed at the top, create a vacuum, and however high up the mercury travels, I should do it this way, however high up the mercury travels is an indication of the atmospheric pressure. Okay. Now I think this is kind of clever. So the difference here, or what's being done, is basically you're putting a less dense material from your syringe, this is weird to me, you're injecting it up through your liquid mercury, and it's less dense, so it kind of makes a puddle on top of your liquid mercury. Again, we're going to talk about volatility, but if something's volatile, basically it evaporates pretty good, okay, vaporizes pretty well. So it's relatively volatile. So notice that now, instead of basically a certain amount that's displaced because of atmospheric pressure, notice we have more displaced, more mercury that's displaced. The difference there is actually the pressure that's being exerted by that volatile liquid that's put in there. That's it. That's it. Okay. And this one kind of shows you that no matter if I kind of doused it with a lot of my volatile liquid or doused it with just a little bit, how would you describe kind of the mercury displacements between B and C?
They're the same.
They're the same, yeah. Bottom line, it kind of goes back to that equilibrium. Once it's established an equilibrium vapor pressure, now at equilibrium, and I could go back to the jar bells things that we looked at before. At equilibrium, you still have condensation and evaporation. It's very dynamic, but the rate of condensation is equal to the rate of evaporation. Okay, so if something's going to condense, something's going to evaporate. It's a one-for-one tit for tat. So yeah, and the way mercury barometers work, we kind of looked at this before, liquid mercury barometers, is it doesn't matter the diameter of the glass tube you chose. So this one right here just makes the diameter smaller. Now one more scenario. I told you that the established equilibrium vapor pressure is temperature dependent, and that's actually what this is doing. I'm not sure I would want to apply heat to liquid mercury, but that's just me, okay? So we apply heat. What do we know about, forget about up here, what do we know about kinetic energy when you apply heat to matter?
Like the pressure increases.
Kinetic energy, I'm not, yeah.
They get more
Pressure increases,
excited.
but I was after, yeah, they get more excited, exactly. And if they get more excited, they can, if this is my liquid phase, if they get more excited, they can go ahead and slip those intermolecular bonds and go from a liquid to be a gas. So a new equilibrium vapor pressure will be established at this higher temperature. Assuming you take the flame and somehow you can kind of level it out, okay, you know, where you're just kind of maintaining the same temperature of that volatile liquid, it's going to establish a new. So what happened to the pressure inside of that top? It increased, yeah, exactly. Very good. Now these kind of talk you through, do you have anything to fill out here? These are all just kind of the same. Okay. Great. So we good with that?
That is a magic handle.
It is. Couple of videos, and I think I'll leave these okay.
In a closed container, molecules
Oops.
move back and forth between the liquid and gas phase.
Where'd the video go? I think I can do this. There we go. Ready?
In a closed container, molecules move back and forth between the liquid and gas phases. If the rates of crossover are equivalent, the overall amount of substance in each phase remains constant. The system is said to be in a state of dynamic equilibrium.
So here's one for you. I was thinking of you guys coming into school today. So what did we have coming into school? We had fog, right? So fog, you guys maybe already know, is actually water that has condensed. So at any given time, you have a certain amount of water vapor, okay? But when you see it cloudy like that, it's no longer a gas or a vapor, it's a liquid, okay? So here's the deal. When you, how do I say this? When it gets foggy like that, basically you have saturated, the air cannot hold all the liquid water that it's, sorry, all the water vapor that it's holding, and some is liquefying. So, something like that. Okay. Here's the second one.
The liquid in the butane lighter is in dynamic equilibrium with the gaseous butane, which has a vapor pressure of about 2.4 atmospheres. When the valve is opened, butane gas escapes from the lighter. The system goes out of equilibrium, and liquid butane rapidly evaporates into the gas phase. When the valve is closed, the system quickly comes to equilibrium again, with the pressure of the butane vapor equal to 2.4 atmospheres.
And that's pretty hefty. 2.4 atmospheres is the pressure of the butane inside there. So what's do you guys, in terms of atmospheres, that's 2.4 atmospheres. How many atmospheres do we have as we kind of walk around the room? 1, yeah. So, and one of the things about gases is they will always go from high pressure to low pressure, and so that's kind of why you have it breathing like that. Okay. So, makes you look at your Bic lighter a whole lot differently. No, I'm just kidding. Okay. Volatility. Okay. So let's see. Oh, it's not. Hold that thought. I got to fix this. Go away. Oh, come on. You guys trying to get it and I keep making it go away? Hang on. Well, you can kind of see it, so. Here we go. That should work. Final answer. I'm done pulling it from you. Okay. So volatility. Volatility, like I said, is kind of the tendency for something to evaporate. Like isopropyl alcohol, very volatile.
Yeah.
Okay. And the volatility has to do with intermolecular bonds. Okay. So the more likely something is to go into its gas phase, we say it's relatively volatile. One of my things, I think I said this in Chem 1, is that if you can smell something, that means that that was a liquid, that means that it turned into a gas, and it basically, you are processing it in your body. So when you gas up at the pump, okay, put gas in your car, if you can smell it, that means it's gone from a liquid to a gas. Pretty volatile, right? So I'm going to draw a couple of beakers here. My beakers, they haven't gotten any better. Okay, here's a beaker. I'll call this A. And here's a beaker. I'll call this B. Because as I was looking at, this is my best way to kind of interpret this. I'll put 2 liquids in there, 2 different liquids, A and B. Okay, and I'm going to go ahead and put watch glasses over there and just kind of pretend, well, I can measure the pressure. Now, when we deal with gases, I think I've mentioned this before, the gas of interest sometimes is easier to find than others. So I'm going to go ahead, and if I do have a watch glass over that ceiling, where it's green, that's hash marks, that is my gas of interest. Okay, and I'm going to measure the pressure, basically. And all this says is assuming T of A, temperature of A, is equal to T of B, okay, assuming that, then if A is more volatile, you know, and this makes sense. If you give it enough time and let it go ahead and reach its equilibrium vapor pressure, then P is going to be greater than A. A is going to be greater than B. Pressure of A is going to be greater than pressure of B. And by pressure, I mean the equilibrium vapor pressure. Makes sense, right? And if I was going to show that, I guess in the past what I've done is I would show more gas particles over here. My gas particles are orange. And fewer gas particles over here. More volatile. And I'm going to go ahead and under more volatile, I'm going to go ahead and say, would the intermolecular bonds be stronger or weaker if it's more volatile?
Weaker.
Weaker, right. I'm going to go ahead and add that to it. Weaker, I'll put IM for intermolecular bonds. Weaker or fewer, same thing. Cool, that's it. And then the next one says, okay, I'll draw my 2 beakers again. And I'll put A and B. And these are, it's kind of have a different scenario. I'll make smaller beakers. There's my watch glass. Oh gosh, they're getting worse. This is substance A and this is substance B. And here's my liquid. Notice in this scenario, we're going to make them at the same equilibrium vapor pressure. So I'm going to go ahead and I'll put 6 dots over there, and I'll put 6 dots over here. Okay? And this goes back to when we lit with we took our flame and lit the volatile substance in your liquid mercury barometer. Okay, it increased, yeah.
I thought volatility is the measure of how easily a liquid is converted to a gas. So now we're measuring the volatility of a gas.
We're measuring the volatility of substance.
Oh, okay.
Yeah.
I was confused.
Yeah. The gas with the substance with the lower temperature will be more volatile.
Because it's like common sense, I would think liquid with a higher temperature would be more volatile, right?
The one where you have to jack up the temperature is going to be less volatile because you had to jack up the temperature.
Okay.
Yeah. So in this one, our goal is to get the same equilibrium vapor pressure.
Okay.
And I'm just going to go ahead and I'm going to go ahead and say A is more volatile again, kind of like we did before. And if I've changed my objective, if I'm not going for different equilibrium vapor pressures, the same equilibrium vapor pressure, can you see where actually the temperature, pick red, the temperature of B needs to be greater than the temperature of A
Okay.
because it's less volatile. Yep. Yeah, so if you want to change this to the substance, you can. And when we're talking about volatility, we are talking about it going from a liquid to a gas. Okay with that? Oh, so I need to add one more thing to this. In this case, I'm going to say pressure or equilibrium vapor pressure of A is equal to the equilibrium vapor pressure of B, but they're different substances. Yep. Okay. Whew. Hey, we're coming up on a problem coming up here in a minute. That's kind of fun. We haven't done one of those for a while with hardcore numbers. Okay. So these are equilibrium vapor pressure curves. And I think a good way to look at this is there are, 5 different substances here? And I guess I'm going to go ahead and show you the different substances. Okay. So the way you read equilibrium vapor pressure curves is we have pressure here and we have temperature we have pressure along the y-axis, temperature along the x-axis. And so C, if you find the black line, that's water. Okay. Diethyl ether looks like that. Diethyl ether. Now, to work these problems, I'm kind of laughing because you're going to have to bring in what we already talked about so far in Gen Chem 2. Okay, you're going to have to bring in the whole polarity thing. So there's kind of the general structure of diethyl ether. Remember, those hydrogens are kind of branching off the carbons. Okay, anytime you see carbons and hydrogens, think nonpolar. Anytime you see an oxygen, think, might be polar. Okay, but we have a little bit of symmetry there, and with symmetry, we bring nonpolarity. Okay, so that's kind of what we have, diethyl ether. Benzene looks like this. And this actually is C6H6. There's benzene. And we'll be talking more about how do you kind of relay what a molecule is. But think of carbon, 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 carbon. This is my C6H6, benzene. And then think of each one of those carbons as having a hydrogen singly bonded. I think I talked about this in Chem 1. But the reason that they go ahead and have a hexagon with a circle in is because actually there's alternating single, double, single, double, single, double. Not bad. Okay, and then I just kind of haven't drawn the carbons and the hydrogens. And it's in resonance with an alternate form, and it goes double here, single, double, single, double, single. So the difference between those two is basically the location. The carbon that has the double, the single was kind of changed. Yes. So anyway, and so to kind of show those two isomers, it's really cool. It's benzene, as bad as it is for health, is really kind of neat. Okay, so that's benzene. And then D is toluene. Toluene is a benzene with a little hydroxyl group on it. Oops. So toluene looks like my build's kind of got, looks like this. That's my toluene. Okay, and then aniline is benzene with a methyl group on it. See if this got on there. No, gosh. And a methyl group is a CH3. Sorry, so that's my aniline.
And it's looking like somewhere with 45 or 50 degrees Celsius, both toluene and water have 100.
So what he's saying is, he's kind of looking at the curves. What temperature did you say?
It looks around like either 45 or 50.
45, 50 here.
It's literally right in between, yeah.
Yep. They behave similarly. Yeah. Yes. So what this, the way you read this is at, let's say 50, at 50, both of these substances, equilibrium vapor pressure is 100 millimeters mercury. That's how you read that. Yeah.
That toluene,
Toluene, yeah.
toluene, it's still got the C's and then the H's and then the CH3 attached to one of them, right?
Aniline does. This is aniline.
Oh.
Yep, and the toluene was an OH. But yes, in both
Oh, an
cases,
OH,
in both cases, there's a carbon here, and this is a carbon for 3 hydrogens. This is a carbon, and this is an oxygen hydroxyl group.
Oh, it has an OH.
Mhm.
That explains
That's
why.
toluene.
That explains why it behaves like water.
Yep. So what he's saying is, if you look at the green line, it's got the hydroxyl group, and notice that the green line is significantly different than the blue line, which is benzene, because of the hydroxyl group.
That explains
It
why
behaves
like
differently.
water.
Mm-hmm.
It has an OH group in it.
Yep. And for each one of these, this is an equilibrium vapor pressure curve. And this probably, I think, will work pretty much for you. But if you have a curve like this, okay, I know it's like the but kind of on the upper left-hand corner, think of it as gas. And on the other side, lower right-hand corner, think of it as liquid in its liquid phase. And that'll be more apparent when we talk about, what is it called? The phase diagrams that have the liquid and the gas and the solid. I don't know if I did that right. Maybe I didn't do that right. Okay, let's move on. So this data in tabulature form actually lines up with the curve you saw for water. This is just for water. Okay. So if it's about 20, well, let's say it's 23 in here, okay, the equilibrium vapor pressure of water is 21.07 millimeters of mercury. Okay, that's an equilibrium. So if you were to put a pan of water here in the center of the room, or go ahead and liquefy it, close the door, seal it up, give it some time, let it establish equal amount of evaporation and condensation, make ourselves a terrarium, right? Okay. At equilibrium, it would be that 21.07. It'd be the pressure that those water molecules in their vapor form would be exerting. Okay, here we go. Let's work a couple problems. Okay, so I think I'll make, how would we do for markers? These problems, and the ones that you're going to work this weekend, I really think need a picture, I think. So I like to use Erlenmeyer flasks for these instead of beakers. I don't know why. Here's my Erlenmeyer flask. And I'm stalling, right? I'm going to go ahead and I'm going to stopper it up. Here's my stopper. Okay, and it says 0.110 grams of liquid is placed. Okay, so I'm going to go ahead and make a puddle down here. Okay, and I'm going to go ahead and call that 0.110 grams H2O. I'll go ahead and put an L for liquid. It's placed, my volume of the container, V is equal to 5.35 liters. Okay, says it's filled with dry air. So all that means is when I start this process, there's no H2O in it. Okay, and it says my temperature is 25 degrees Celsius. All right. Then here comes the question. It says verify that under these conditions all of the water will evaporate. So I'm going to put my water and I'm going to say question mark, all will evaporate. Okay, now in context of what we've just been talking about, do you buy this that if I evaporate all my water, I'll put it this way, as I evaporate my water, I'm going to go ahead and these are going to be my water molecules, now in their gaseous state. Okay. Do you buy this that if I go ahead, how do I say this? If this vapor pressure, I'll put P of H2O, question mark, okay? If this vapor pressure is less than my equilibrium vapor pressure of water, I'll put P H2O EVP, equilibrium vapor pressure, okay? If this is less than my equilibrium vapor pressure, then I can keep going till the cows come home. I'm not done. I still have room to evaporate more water. That's it. That's actually the approach we're going to take. Okay. Well, the way we're going to work this basically is we're going to assume all, and by all I mean that 0.110 grams H2O, assume all of it goes from liquid to gas. If all of it goes from liquid to gas, I can now come up with my pressure of my H2O by using PV is equal to nRT. This is where I was thinking, I love this phrase. You know, for people, a lot of people love gas law problems. I know. We did them at the end of Chem 1. And this is where Chem 1 intersects with Chem 2. Okay? So at this point, if it all evaporates, okay, we know the volume. We were given the volume. We know if it all evaporates, we can take that mass and get N. Of course, R is the constant you look up. And T was also given. That's it. Okay. We're going to assume ideal gas law behavior. So this is where we're going to have to take the 25, okay, and we're actually going to compare our pressure that we get to this pressure. So 23.76 millimeters of mercury. So this is the strategy we're going to do. There's two strategies, okay, and I hope, I don't know, if you, we're going to work two problems, and on the next problem we're going to actually use the other strategy. So we're going to calculate the theoretical partial pressure of water, okay, theoretical partial pressure of water, assuming that it all evaporates, okay. Now, if it all evaporates, okay, we're going to compare what we get to that equilibrium vapor pressure on the table. And if it comes in under it, then we actually know we didn't bump up against the equilibrium vapor pressure. We could have actually evaporated even more water. Okay? Then all the water will evaporate. The second approach, and actually we're going to take this on the second problem we're going to do here in a minute, is to go ahead and calculate, go ahead and assume that this volume at this temperature is what we call saturated. Go ahead and assume that the pressure of the water is that equilibrium vapor pressure we saw on the table. And then we're going to backtrack using PV equals nRT again to get what the moles then would have been, and then backtrack that to mass. And in that case, if the mass is less, in this case we would see that the mass would be greater. If the mass is greater than what we had to evaporate in the first place, then we know that we were undersaturated and it will all evaporate. So that's kind of what we got going on. Okay. So the reason that we're using the first approach is because we were given a hint. It basically said, assume, or it said, how can you prove that all of it will evaporate? And that was our hint to go ahead and go with the first approach. But the second approach should work too. Okay, here we go. So we're going to calculate the pressure that would be exerted if all of this water evaporated. Yep, you got to put on your Chem 1 hats. So we're going to use the ideal gas law equation, and we know everything except for P. But we have a little bit of background stuff to do. We can rearrange PV equals nRT to solve for P, and that's equal to nRT over V. I think I mentioned in Chem 1 that this is where most of us make, or a lot of us make mistakes, is this simple algebra. Rearranging PV equals nRT. Divide both sides by V, and that's what you got. We have some fixing up to do, okay? One of the fixing ups is to go ahead and take, we have to get N, and we get N from the mass of water. So I was a big stickler, and I still am. You have to know the molar mass of, you have to show me calculating the molar mass of water, which you probably know, commit by memory, 18.02 grams per mole. So if our first term is mass, 0.110 grams over 1, then we use the flipped version of the molar mass, 1 mole of H2O over 18.02 grams of H2O. We get moles of H2O to 3 significant figures. So in Chem 2, you're going to have to keep track of your sig figs, allowing for 3 significant figures, 0.00610 moles of H2O. So that's going to be our N. So remember, we have to get 3 significant figures, we do one of those trailing zeros after the decimal. Just the other day we were talking about that, right? So that's our N term. We have a little bit more fixing up to do, which is kind of common with using the ideal gas law equation. Okay. We need to fix our temperature from Celsius to Kelvin, and we need to add 273 units for that. So we're looking at 298 Kelvin, and that might be about it. Our volume was already given in liters, so that's perfect. Volume is 5.35 liters. That was the volume of our Erlenmeyer flask. It had to be an Erlenmeyer flask, but. So now we plug and chug, but it's like Chem 2 is like Chem 1, where you have to show all of the units. And units will allow for things to cancel. So now we have the pressure is equal to N, which is 0.00610 moles. Also in the numerator then is the term R. That's that 0.082058. Units of R are liters, atmospheres per mole Kelvin. Also in the numerator is temperature, so 298 Kelvin. In the denominator, all we have is the volume, which is 5.35 liters. So allowing terms to cancel, I got in the numerator, I have moles canceling with moles, units of Kelvin canceling with Kelvin, and then looks like I have units of liters canceling between the numerator and the denominator. So we just have atmospheres, yep. But do you guys buy this here in a minute? When we compare it to our equilibrium vapor pressure at that temperature, we're going to have to do some conversion somewhere, because that was in millimeters of mercury, and this is in atmospheres. There actually is an R out there that is in units of liters, millimeters of mercury per mole Kelvin. But rounding to 3 sig figs, the pressure then, if all of that H2O evaporates, is going to be 0.0279 atmospheres. Again, then you can't compare it directly because you kind of have atmospheres and millimeters of mercury, but we're close. Can't remember what I did in my notes. So I'm going to go ahead and convert atmospheres to millimeters of mercury so I can compare it with the table. So if I remember, there's a 1 atmosphere is exactly equal to 760 millimeters of mercury. So if I start with the term 0.0279 atmospheres over 1, and I put 760 millimeters of mercury over 1 atmosphere, units of atmosphere will cancel. I left with units of millimeters of mercury. Notice that since there's an exact relationship between atmospheres and millimeters of mercury, that brings no uncertainty. So we're still allowed 3 significant figures, and I get 21.2 millimeters of mercury. So finally now, we're ready to go ahead and compare that pressure with the equilibrium vapor pressure at that temperature of water. And here we go. So notice that since what we got, if it all evaporates, is less than the equilibrium vapor pressure at that temperature, then all we did was answer that it will all evaporate. This is one of those questions that if you get on test, you're like, well, yes or no, but you have to show, okay, this is proof. So I've looked at the homework, and I do have hints to give you that you're going to be doing over the weekend. And the problem with these problems is that they are so assorted, but if you draw a picture, you got a fighting chance of working it out. Okay? Now, if you had come up with, if all that water evaporates, then that your partial pressure of water vapor is greater than your equilibrium vapor pressure from the table at that temperature, then you say, dude, it can evaporate, but it's not all going to evaporate, okay? It would basically, you'd have a puddle left. You'd have liquid left.
Will we have a problem where we'll have to convert Fahrenheit into Celsius and then Celsius into Kelvin?
No. We're metric.
I remember one was in first semester that they kind of threw us for a loop on the assignment slide.
Oh, yeah.
Because you had to convert Fahrenheit into Celsius and then the Celsius into Kelvin.
Okay. So, another picture, another problem, another day, another picture. So I'm going to go ahead and, like I said, I like Erlenmeyer flasks. I don't know why. I don't know why. Maybe it's because I can't picture that a watch glass really can seal a beaker. You're like, are you serious? I know. But I can picture a stopper at the top. So in this one, the picture's going to look different. Here's my Erlenmeyer flask. It almost kind of looks like my volumetric flask. I'll go ahead and stopper it up. And I'm going to put, again, the substance is water, but it wouldn't have to be. Again, we're going to deal with water, and it's 1.25 grams of H2O in its liquid state. And my volume is a big one. I'm going with 9.70 liters. Okay. Again, the dry air just means that when we start this puddle to evaporating, there's no other water molecules in there. My temperature is jacked up. Instead of 25, it's 40 with a decimal degrees Celsius. So I have a note to the nearest ones there. So then here's the question. Verify. So again, verify is going to help us, okay? Verify that under these conditions, not all of the water will evaporate. And then the follow-up is determine the partial pressure of the water vapor in the flask at equilibrium. That's dull. We just picked that off the table, okay? And then also calculate your puddle that's left. Calculate the mass of water that you have that didn't evaporate. So in other words, this is going to evaporate, okay? I'm going to have an equilibrium vapor pressure. I'll put P, E, V, P, equilibrium vapor pressure of H2O. Okay, again, to me, answering that first question, if you're like, well, we're just going to look at the table, you are. Okay, whatever that is from the table, okay? And whatever is, we need to know, I'll put question mark, mass remaining. Mass H2O liquid left. Left is easier to write than remaining. Okay. So in this case, if we look at our options, okay, by the way, we're dealing with 40. 40's not on there, so actually we can kind of estimate between the two or pick it off of somewhere else. And I think I pick it off somewhere else. We can also pick off, use 40 and find our black line, which is water. and pick off the equilibrium vapor pressure there. Got some options. Options are good. Okay, so this slide is identical to the slide before with our potential strategies. Okay, so the first one doesn't make as much sense as the second one. Down here, this is what we're going to do. We're going to calculate the mass of water that would be contained if I go ahead and have this at its equilibrium vapor pressure, that volume, that temperature. I'm going to basically say, forget the puddle, I'll say, what's the container, the temperature? How much water will be there at the equilibrium vapor pressure? Okay? And then I'm going to compare that mass with my puddle. And we're going to find out that that mass is going to be less than my puddle that I start with. Okay? And so then by difference, I'm going to take that mass, and I'm going to subtract that from my 1.25 grams. I know. It kind of hurts my brain too. So, what's that?
Instead of having the volume underneath the fraction, you'll have pressure underneath the fraction and volume would be remaining.
Probably. I'd have to, rearrange the ideal gas law equation. It will be different.
Okay.
Yeah. Yep. Okay. So, yeah, we're going to solve for n this time. Okay, we're going to solve for number of moles. Okay, that would be there at the equilibrium vapor pressure. Now, the first question was, what is the pressure of your water? What is the equilibrium vapor pressure in that container at that temperature? Yeah.
Do we need to memorize any of the stuff on the table for tests, or
No. No, these, I will always give you these values. It's not like the density of water is, what, 1.00 grams per milliliter. You need to still memorize the density of water, but none of these. Yeah. So there's a table, and I don't think I didn't pull it up, but in your textbook that you can pick off for water, 40 degrees, what's its equilibrium vapor pressure. So actually that's the pressure we're going to use in our PV equals nRT, solving for n. But in order to use the R that we're using, we need to convert those millimeters of mercury to atmospheres. So here we go. We know that there's how many millimeters of mercury in one atmosphere?
760?
Mm-hmm. 760. So that looks like this. If we start as our 55.3 millimeters of mercury over 1, we can multiply it by 1 atmosphere divided by 760 millimeters of mercury. And millimeters of mercury cancel, we're left with the atmospheres. Remember that there's no uncertainty brought by this ratio because this is an exact equality. So we round to 3 significant figures. And I got the pressure then, equilibrium vapor pressure of water at any temperature, in any container at the temperature of 40 degrees Celsius is 0.0728 atmospheres. Okay, so that's going to be our P. And if we rearrange PV equals nRT, we divide both sides by RT, okay, and kind of move things around, and we get N is equal to PV over RT. And I think maybe this is what you were talking about.
Yeah, I was wrong though.
Oh, I always have to write it out. So let's go ahead and substitute what we know. The pressure we already fixed is 0.0728 atmospheres. The temperature we still need to fix, if we take 40 with a decimal after the 0 plus 273 units, we get 313 Kelvin. Our volume was given in the problem as 9.70. So don't forget your units when you work these out. So in the numerator we have PV. So in the numerator we have 0.0728 atmospheres times 9.70 liters. And the denominator we have RT. So in the denominator we have 0.082058 units for that R are liters, atmospheres, over moles, Kelvin. And then also in the denominator we have temperature, which was that 313 Kelvin. So looking at what things cancel, that looks like this is where we have atmospheres and the cancel. I guess it's not so complicated. Liters cancel, Kelvins cancel, and now we have moles in the denominator of the denominator, which makes them in the numerator of the numerator. Units of moles rounded to 3 sig figs. We got moles as 0.0275. 0.0275 moles of H2O. Phew! Now, in order to compare that, moles, to this mass that we had originally, we got to convert that to mass, yeah. So we can do that using the molar mass. So if our first term is the moles, that 0.0275 moles H2O over 1, then we use the 18.02 grams of H2O for 1 mole of H2O. Round to 3 sig figs, drum roll. And then this is the mass then of H2O that would be floating around. If you could condense it back down again and weigh the little critters. 0.495 grams. So clearly it's less than our 1.25 grams. And we're almost done. One quick subtraction at the end. Okay? So here's our subtraction. Now since we're subtracting, we round according to decimals though, right? So in the first term, the mass we had given the problem, we have 2 decimals here, and we have 3 decimals here in the mass that we came up with of water that will evaporate. So we're only allowed 2 decimals in our answer. I didn't switch rules between Chem 1 and Chem 2.
Nope.
They're the same rules. Okay? So let's take a quick look at the assignments that's due. Looks like Monday. Monday, da, 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 da. Oops. And it starts with, what's the first one? 12 point.
29.
Thank you. Okay. Here we go. Oh. Oh, it is 30.
Yeah, we got 29, 30, 33, 34, 35, and 36.
Okay. Well, let's do this first. Thanks for pointing that out, though. Oh, that isn't what I meant to do. This is what I meant to. Yeah. Okay. So, density is given. Now, that density is actually grams of grams of acetone vapor per liter. So now we're switching gears. We're not dealing with water. Now it's acetone. There's my famous Erlenmeyer. If you read it a few times, I think what works well is if you assume basically you have an Erlenmeyer that's saturated with regard to acetone, and then you can go ahead and use that density. We did this, I think, in Chem 1. We're going to set as our basis 1 liter. You get to pick. So I picked the volume of my Erlenmeyer as 1 liter. If that's the case, then I must have 0.876 grams of acetone vapor present. And then things kind of fall into place.
We have to express it in kilopascals.
Oh, yeah, thank you. Not just, you're using PV equals nRT, you're getting it in atmospheres, and to take it all the way, you need to get it in kilopascals. Okay, so there's my hints for that one. Oops. Here's my hints for the next one. The next 2 are not so bad. The next 2, you're using this table, and it basically says, pressure cookers, the way they work is to increase the boiling point temperature. So at a pressure of 2 atmospheres, what temperature does water boil at? So basically you convert 2 atmospheres to millimeters of mercury, and then you find that on here to find the boiling point temperature. And remember, those are in units of Celsius. All right.
And 1 atmosphere is 760 millimeters of mercury.
Right,
So.
exactly. And this one you use the table too. It says that you guys know if you go up or down in elevation, the pressure, atmospheric pressure changes. So as you go up in elevation, the pressure decreases. So instead of being 760 millimeters of mercury, you're looking at 640 millimeters of mercury here. Again, what does the boiling what would be the boiling point temperature of water at that higher elevation, that lower pressure? Now in this one, you don't have 640 on there, so I kind of highlighted where I would kind of just estimate.
It's basically gonna be 95 point something.
Mm-hmm. And then there's a follow-up question, says the temperature of water boils at 94 degrees Celsius at this location, so what atmospheric pressure must it be? Okay, so use the table again. Now these other ones are a little more interesting. This is describing basically using helium carrier gas to go through a chamber that has liquid aniline. Remember, aniline is the benzene ring with the CH3, okay? And then the way I drew it is it's going to basically kind of congregate over here in a third chamber. This third chamber is going to be a mixture. It's going to be your carrier gas helium, and it's going to be the aniline that it picked up, okay? It goes ahead and gives you can kind of see where I wrote what you know about each thing. What do you know about the helium? What do you know about the aniline? Okay, and what do you know about this chamber over here? So I don't want to keep you guys too long, but there's my hints.
You always tell these on my Twitter, right?
I do. Oh, come back here. Click the wrong button. There's the next one. It's kind of similar. Have a carrier gas. Now, it's not aniline. It's carbon tetrachloride. Okay, I know. And then here's the last one. The last one gets back to being a little bit easier, I think.
Yeah.
No
it's
carrier
29.
gas. Yeah, we have liquid bromine. It establishes an equilibrium in Erlenmeyer. Okay, so you should be doing fine. Now, I think I have 12 too, so I'll just kind of post that. I must have, or 29,
That was
yeah.
29.
That was 29?
Yeah.
Oh, there you go. It's on the end. Okay. So, very good.